Greetings, my name is Jiajing Qiu, and I will be giving a talk about the paper on behalf of my schoolmate Delong Zhang. The paper is titled on Temporal Verification of Stateful P4 Programs. In the very beginning, let's go through some of the basic background information about SDN, or software-defined networks. To overcome the shortcomings of traditional network, SDN emerges. It divides a network into the control plane and the data plane, offering centralized control and remarkable flexibility. In addition, P4 is a domain-specific language designed for data plane programming. Unlike traditional network devices that rely on fixed protocol processing like TCP or UDP, P4 is a protocol-independent description language that facilitates developers to implement their own packet processing needs. More specifically, this slide illustrates a minimal P4 program. So when a packet arrives, the first thing is to make sense of the contents of the packet. That is done by the header block, which defines the structure of packet headers, and the parser block, which extracts the header according to the structure defined above. After parsing the packet, we should decide what to do with the packet. Should we actually forward the packet or drop it? To do this, we need a table block, which defines match action rules for the packets, and the control block, which uses the table and other custom logic to control the destiny of a packet. And together, they form the processing logic of the data plane pipeline. And here's an illustration of how a P4 program works. A P4 program is executed for each incoming packet, and a special stateful memory called register is used to persist state information across processings of multiple packets. And here comes the topic of the paper. It lies in the verification of such stateful P4 programs utilizing registers. Program verification, firstly, is of great importance, especially for network functionalities. For instance, faulty routers once grounded airline for days, resulting in millions of dollars of losses. And therefore, numerous P4 program verifiers have been developed. But unfortunately, we have discovered that these existing P4 verifiers have a little bit of overapproximation about the stateful memory registers. Existing models only check the processing of a single packet and assumes that the register variables are fully non-deterministic. However, this level of abstraction overlooks the stateful nature of packet processing, where register values in fact persist and are preserved for subsequent processing of packets. For instance, consider the simplified code example of BNRist, which is an eavesdrop defense mechanism implemented in P4. So as shown in the code, the mechanism simply distributes a flow circularly to port 1, 2, 3, and back to 1, 2, 3, and so on. Well, to achieve this, it uses the register called count to record the port that the last packet is sent to. So suppose that we need to now enforce a safety rule. We aim to check that the above code introduces no implicit drop. That is, the egress back variable in the code snippet above must be set. When count the register is initially configured with 1, 2, or 3, actually the property is satisfied. But on the other hand, when count is initially set out of the valid range, for instance, let's say 4, it will bypass all the conditional checks in the code and result in the property violation. However, existing verifiers cannot do this level of analysis. Even when we know that count is configured to be a safe, valid number, for instance 1, they will still report the property as unsafe because they treat the register values as fully non-deterministic. Moreover, let's consider another liveness property concerning load balancing. So the liveness property states that when valid packets arrive infinite often, every valid port should be activated infinitely often. And unfortunately, prior P4 verifiers struggle to check such liveness properties due to their inability to track network states. So to properly verify the properties that we exemplified above, here we face several challenges and we will detail them. The first challenge is how to model the stateful nature of P4 programs. To model the stateful nature of packet processing, we treat a P4 program as a procedure invoked within an infinite loop. As shown in the pseudocode, we explicitly model the infinite execution of a P4 program instead of a single packet linear processing. Each iteration of the loop represents one processing of a packet. The values of the registers are initialized at the very beginning of the procedure and retained after each packet is processed in the loop. This approach allows us to view the execution as continuous and correlated instead of isolated, capturing the stateful behavior of the system across successive packet processing. And here is challenge 2. How to specify temporal properties of P4 programs at this level of packet processing. Specifically, we adapted LTL, which means linear temporal logic, to model the stateful behavior of P4 programs at the packet processing level, and propose our domain-specific construct named P4 LTL. The basic part, which is terms of P4 LTL, mainly consists of integer numbers, packet headers H, and metadata M, and free variables V, and so on. They represent the values of these P4 basic terms at the end of each packet processing. And in addition, for the predicate part, they are defined over our P4 LTL terms and are used to describe packet forwarding behaviors of P4 programs. For instance, predicate FWD, which means forward, is true if the packet is forward to port T at the end of packet processing. And predicate valid is true, valid H is true if the corresponding header H is valid after the passing progress, etc. And next, we move on to our LTL construct. The LTL component is the key part of P4 LTL. To specify the behavior of stateful P4 programs, that is, how packet sequences are processed, we define our semantics at the level of packet processing. For instance, consider operator next, which is denoted by a circle before the predicate. It is satisfied when the condition holds true at the end of next processing. As for operator eventually, which is denoted by a diamond, it is satisfied when the condition holds at the end of some packet processing eventually. And for operator global, which is denoted by a square here, it is satisfied when the condition holds at the end of every packet processing. And with the constructs of P4 LTL, let's go back to the properties we talked about earlier. The liveness property, for instance, can be expressed in P4 LTL as shown below. And here's the formal definition of P4 LTL semantics. A trace tau satisfies a P4 LTL specification phi is written as tau models phi. A P4 program now satisfies a P4 LTL specification phi if and only for each and every trace tau of P, tau models phi. And here is challenge 3, how to verify temporal properties of P4 programs. First, about some background about how regularly we check LTL properties in regular model-based checking. Normally, we build a product automaton from the program automaton and specification automaton. And this product is called Büchi program product. The Büchi program product represents all counterexample traces that violate the property. And then we can check whether the product automaton recognizes empty language using the well-established framework in automata theory. If the Büchi program product recognizes an empty language, it means that there is no counterexample trace for the property, and then we prove that the property is satisfied. Otherwise, we can find a property, get a trace from the product, which represents a counterexample. However, this classic strategy cannot be directly used in P4 LTL. And the reason is that in Büchi program products, the program automaton and the specification automaton are combined synchronously on a per statement level. That is, every time a program automaton advances, the specification automaton also advances, according to the small timestamp, that is per statement. However, the time step of P4 LTL is defined on a more coarse level. It is defined on the execution of a whole P4 program rather than its individual statements. To verify program-level temporal properties, then we must align the different timestamps of the big timestamps and small timestamps. Therefore, to align the timestamps and enable verification of P4 LTL, we propose a novel concept called Büchi transaction. The primary difference between Büchi transaction and the existing Büchi product is that it is in the transition part, is in the product operator part. So Büchi transaction combines the automata asynchronously. That is, the specification automata ticks only when the whole transaction finishes, rather than when a single statement is executed. For P4 LTL, the transaction is the execution of a P4 program. And under the definition of our Büchi transaction, we can now conclude the following theorem. That is, the P4 program P satisfies the P4 specification phi if and only if the corresponding Büchi transaction does not have any fair and feasible trace. With the theorem, we can now check P4 LTL by checking whether the Büchi transaction recognizes any empty language. And the proofs are detailed in our paper. And now let's take a look at our evaluation part. We have implemented our prototype and named P4TV and compared with state-of-the-art P4 verifiers, including BF4, P4V, Veri, and Aquila. We experiment to answer the following questions. And the first question is, how can P4TV verify temporal properties of Stateful P4 programs? As P4TV pioneers temporal verification for Stateful P4 programs, we introduce a dedicated dataset tailored for this purpose. The dataset comprises 9 non-trivial Stateful P4 programs sourced from both the open source community and academic papers. In total, we formulate 19 stateful verification tasks containing safety and liveness properties and also the satisfied and not satisfied properties. And the result is that P4TV successfully solves all of the tasks, while every existing verifier failed to verify these temporal properties because they don't support temporal verification of temporal properties at all. And next, we move on to the next question. How does P4TV compare with state-of-the-art priors? P4 verification priors primarily focus on program assertion verification, which is a special case of P4 LTL. And when comparing with other state-of-the-art P4 verifiers, P4TV effectively confirms safe assertions and reports genuine counterexamples for unsafe ones. However, for priors, which assume registers entirely non-deterministic, they return spurious counterexamples due to their overapproximation in their environment modeling. So to conclude, we propose the first approach to check temporal properties in P4 programs at the packet processing level. And we propose a domain-specific language called P4 LTL tailored for it. In addition, we propose a novel concept called Büchi transaction, which aligns the time step between program semantics and packet processing. And that's the end of my presentation today. Thanks everyone for the listening.